language processing? Well, you're doing it right now. You're listening to the words and the sentences that I'm forming, and you are forming some sort of comprehension from it. And when we ask a computer to do that, that is NLP, or natural language processing. My name is Martin Keane. I'm a master inventor at IBM, and I've utilized NLP in a good number of my invention disclosures. NLP really has a really high utility value in all sorts of AI applications. Now, NLP starts with something called unstructured text. What is that? Well, that's just what you and I say. That's how we speak. So, for example, some unstructured text is add eggs and milk to my shopping list. Now, you and I understand exactly what that means, but it is unstructured, at least to a computer. So what we need to do is to have a structured representation of that same information that a computer can process. Now that might look something a bit more like this, where we have a shopping list element, and then it has sub-elements within it, like an item for eggs and an item for milk. That is an example of something that is structured. Now, the job of natural language processing is to translate between these two things. So NLP sits right in the middle here, translating between unstructured and structured data. And when we go from unstructured here to structured this way, that's called NLU, or natural language understanding. And when we go this way, from structured to unstructured, that's called natural language generation, or NLG. We're going to focus today primarily on going from unstructured to structured in natural language processing. Now let's think of some use cases where NLP might be quite handy. First of all, we've got machine translation. Now, when we translate from one language to another, we need to understand the context of that sentence. It's not just a case of taking each individual word from, say, English and then translating it into another language. We need to understand the overall structure and context of what's being said. And my favorite example of this going horribly wrong is if you take the phrase, the spirit is willing but the flesh is weak, and you translate that from English to Russian, and then you translate that Russian translation back into English, you're going to go from the spirit is willing but the flesh is weak to something a bit more like the vodka is good but the meat is rotten, which is really not the intended context of that sentence whatsoever. So NLP can help with situations like that. Now, the second kind of use case that I like to mention relates to virtual assistants and also to things like chatbots. Now, a virtual assistant, that's something like Siri or Alexa on your phone that is taking human utterances and deriving a command to execute based upon that. And a chatbot is something similar except in written language, and that's taking written language and then using it to traverse a decision tree in order to take an action. NLP is very helpful there. Another use case is for sentiment analysis. Now this is taking some text, perhaps an email message or a product review, and trying to derive the sentiment that it's expressed within it. So, for example, is this product review a positive sentiment or a negative sentiment? Is it written as a serious statement, or is it being sarcastic? We can use NLP to tell us. And then finally, another good example is spam detection. So this is a case of looking at a given email message and trying to derive is this a real email message or is it spam? And we can look for pointers within the content of the message. So things like overused words or poor grammar or an inappropriate claim of urgency can all indicate that this is actually perhaps spam. So those are some of the things that NLP can provide, but how does it work? Well, the thing with NLP is it's not like one algorithm. It's actually more like a bag of tools, and you can apply these bag of tools to be able to resolve some of these use cases. Now, the input to NLP is some unstructured text, so either some written text or spoken text that has been converted to written text through a speech-to-text algorithm. Once we've got that, the first stage of NLP is called tokenization. This is about taking a string and breaking it down into chunks. So if we consider the unstructured text we've got here, add eggs and milk to my shopping list, that's 8 words, that could be 8 tokens. And from here on in, we are going to work one token at a time as we traverse through this. Now, the first stage, once we've got things down into tokens that we can perform, is called stemming. And this is all about deriving the word stem for a given token. So for example, running, runs, and ran, the word stem for all 3 of those is run. We're just kind of removing the prefix and the suffixes and normalizing the tense, and we're getting to the word stem. But stemming doesn't work well for every token. For example, universal and university, well, they don't really stem down to universe. For situations like that, there is another tool that we have available, and that is called lemmatization. And lemmatization takes a given token and learns its meaning through a dictionary definition, and from there it can derive its root or its lem. So take better, for example. Better is derived from good, so the root or the lem of better is good. The stem of better would be bet. So you can see that it is significant whether we use stemming or we use lemmatization for a given token. Now, next thing we can do is we can do a process called part of speech tagging. And what this is doing is, for a given token, it's looking where that token is used within the context of a sentence. So take the word make, for example. If I say, I'm going to make dinner, make is a verb. But if I ask you what make is your laptop, well, make is now a noun. So where that token is used in a sentence matters. Part of speech tagging can help us derive that context. And then finally, another stage is named entity recognition. And what this is asking is, for a given token, is there an entity associated with it? So, for example, a token of Arizona has an entity of a US state, whereas a token of Ralph has an entity of a person's name. And these are some of the tools that we can apply in this big bag of tools that we have for NLP in order to get from this unstructured human speech through to something structured that a computer can understand. And once we've done that, then we can apply that structured data to all sorts of AI applications. Now, there's obviously a lot more to it than this, and I've included some links in the description if you'd like to know more. But hopefully this made some sense, and that you were able to process some of the natural language that I've shared today. Processing natural language understanding and natural language generation. NLP, NLU, NLG. What's the difference? Allow me to demonstrate. Now, look, what I just did there is, well, by writing a story, I performed an example of natural language generation. And if you're now peering at the screen, reading it, or even just trying to understand and make sense of what I'm saying right now, you're participating in natural language understanding. And together, you and I are both performing subsets of the overall collective of natural language processing. So, NLU and NLG, they're both subsets of NLP. But we're missing one quite important point here. The natural language processing stuff that we're interested in today is performed by computers, not humans. So when we use these terms, what do we really mean? And how can these models be put to work? Well, NLP enables computers to understand human language in both written and verbal forms using deep learning techniques to complete tasks. Typical examples for that are things like language translation or conducting a conversation in a chatbot. Now, it does this through the identification of named entities, which is a process called named entity recognition, and identification of word patterns using methods like tokenization, stemming, and lemmatization. And I've covered some of this in a previous video about NLP, so we won't go over that in detail here. Let's focus instead on these two things, natural language understanding and natural language generation. So natural language understanding uses syntactic and semantic analysis of text and speech to determine the meaning of a sentence. Unlike structured computer code, our unstructured, messy human language has all sorts of nuances that NLU needs to account for. So let's take a look at a couple of examples. I'm going to come up with some sentences here. So like, Alice is swimming against the current. This is a sentence that we could feed into an NLU algorithm and ask it to really make sense of it. Another example, the current version of the file is in the cloud. So that's two sentence examples. Let's take a closer look at trying to make some sense of these. So we've got the word current here in this first sentence. The word current is a noun, and that's preceded by a verb. The verb here is swimming. Together, that provides additional context to the reader, allowing us to conclude that we are referring to the flow of water in the ocean when we talk about current in this situation. In the second example, here's the word current, and this time it's an adjective, and the noun it describes is version. So that denotes that we've got multiple iterations of a report, and here current is implying that we have the most up-to-date status of the file. So two completely different meanings for current. And understanding the relationships between words and phrases is what NLU is really all about, and it enables us to derive the intended meaning of a sentence. Now, while NLU is all about improving a computer's reading comprehension, NLG, or natural language generation, focuses on enabling computers to write. It's the process of producing a human language text response based on some data input. NLG applications need to consider language rules based on morphology, lexicons, syntax, and semantics to make choices on how to phrase responses appropriately. Now, NLG typically consists of three stages. So if we look at NLG, the first stage is text planning. And text planning formulates the orders and the content in a logical manner. Similarly, we have sentence planning. And sentence planning considers things like punctuation and text flow and breaks out the content into paragraphs and sentences. And then the third stage is called realization. And realization ensures we're playing correctly by the rules of grammar, that For example, we know that the past tense of the verb run is actually ran and not runned. Yeah, that's not right. So NLG is enabled by a variety of machine learning models to perform this stuff, and that includes things like hidden Markov chains, recurrent neural networks, and transformers. Look, natural language processing and its subsets NLU and NLG have numerous practical applications, from healthcare diagnosis to online customer service. Oh, and another way you can use these is in, hey, Lightboard videos. In fact, I asked an NLG algorithm to write me a sentence to conclude this talk, and it said, natural language processing is amazing and has many practical applications, like me. Thanks. And supervised learning are two core components in building machine learning models. So, what's the difference? Well, just to cut to the chase, supervised learning, that uses labeled input and output data, while an unsupervised learning model doesn't. But what does that really mean? Well, let's better define both learning models, go deeper into the differences between them, and then answer the question of which is best for you. Now, in supervised learning, the machine learning algorithm is trained on a labeled data set. So this means that each example in the training data set, the algorithm knows what the correct output is. And the algorithm uses this knowledge to try to generalize to new examples that it's never seen before. Now, using labeled inputs and outputs, the model can measure its accuracy and learn over time. Supervised learning can be actually divided into a couple of subcategories. Firstly, there is a category of classification. And classification talks about where the output is a discrete class label, such as spam and not spam. Linear classifiers support vector machines, or SVMs, decision trees and random forest. They're all common examples of classification algorithms. The other example is regression. The output here is a continuous value such as price or probability. Linear regression and logistic regression are two common types of regression algorithms. Now, unsupervised learning is where the machine learning algorithm is not really given any labels at all. And these algorithms discover hidden patterns in data without the need for human intervention. They're unsupervised. Unsupervised learning models are used for three main tasks. There's clustering, association, and dimensionality reduction. So let's take a look at each one of those, starting with clustering. Now, clustering is where the algorithm groups similar experiences together. So a common application of clustering is customer segmentation, where businesses might group customers together based on similarities like, I don't know, age or location or spending habits, something like that. Then you have association. And association is where the algorithm looks for relationships between variables in the data. Now, association rules are often used in market basket analysis, where businesses want to know which items are often bought together. You know, something along the lines of customers who bought this item also bought, that sort of thing. The final one to talk about is dimensional reduction. And this is where the algorithm reduces the number of variables in the data while still preserving as much of the information as possible. Now, often this technique is used in the pre-processing data stage, such as when autoencoders remove noise from visual images to improve picture quality. Okay, so let's talk about the differences between these two types of learning. And in supervised learning, the algorithm learns from training data sets by iteratively making predictions on the data and then adjusting for the correct answer. While supervised learning models tend to be more accurate than unsupervised learning models, they do require all of this upfront human intervention to label the data appropriately. For example, a supervised learning model can predict how long your commute will be on the time of day and thinking about the weather conditions and so forth. But first you'll have to train it to know things like rainy weather extends the driving time. By contrast, unsupervised learning models work on their own to discover the inherent structure of unlabeled data. These models don't need humans to intervene. They can automatically find patterns in data and group them together. So for example, an unsupervised learning model can cluster images by the objects they contain, things like people and animals and buildings, without being told what those objects were ahead of time. Now, an important distinction to make is that unsupervised learning models don't make predictions. They only group data together. So if you were to use an unsupervised learning model on that same commute data set, it would group together commutes with similar conditions like the time of day and the weather, but it wouldn't be able to predict how long each commute would take. Okay, so which of these two options is right for you? In general, supervised learning is more commonly used than unsupervised learning, and that's really because it's more accurate and efficient. But that being said, unsupervised learning has its own advantages. There's two that I can think of. Firstly, unsupervised learning can be used on data that is not labeled, which is often the case in real-world data sets. And then secondly, unsupervised learning can be used to find hidden patterns in data that supervised learning models just wouldn't find. Classifying big data can be a real challenge in supervised learning, but the results are highly accurate and trustworthy, and in contrast, unsupervised learning can handle large volumes of data in real time. But there's a lack of transparency into how that data is clustered and a higher risk of inaccurate results. But wait, it is not an either-or choice. May I present to you the middle ground known as semi-supervised learning. This is, well, a happy medium where you use a training data set with both labeled and unlabeled data, and it's particularly useful when it's difficult to extract relevant features from data and when you have a high volume of data. So, for example, you could use a semi-supervised learning algorithm on a data set with millions of images where only a few thousand of those images are actually labeled. Semi-supervised learning is ideal for medical images where a small amount of training data can lead to a significant improvement in accuracy. For example, a radiologist can look at and label some small subset of CT scans for tumors or diseases, and then the machine can more accurately predict which patients might require more medical attention without going through it and labeling the entire set. Machine learning models are a powerful way to gain the data insights that improve our world. The right model for your data depends on the type of data that you have and what you want to do with it. And the choice between supervised and unsupervised learning is only the first step.
You reached the end of this video segment. Let me put summary for you. Supervised and unsupervised learning are foundational techniques in machine learning, each offering unique benefits. Supervised learning uses label data to make the prediction and classify data into specific categories, making it ideal for accurate outcome like identifying a spam or predicting prices. On the other hand, unsupervised learning discovers hidden pattern in unlabeled data, often used in applications like customer segmentation and market basket analysis. The video also introduces semi-supervised learning, middle ground between supervised and unsupervised, a blend of both techniques, perfect for handling large data sets with limited labeled information as seen in medical imaging systems. Learn how to choose the best model based on your data and objectives. Here are the key highlights of video. The first is supervised learning, right? How to use the label data to make precise prediction, ideal for classification of, example, spam detection, and regression, example, price prediction. Another highlighted area in this video is unsupervised learning. Discover patterns in unlabeled data commonly used in clustering, example, customer segmentation and association, example, market basket analysis. Another category we have learned in video is semi-supervised learning. So combines both labeled and unlabeled data together, useful for cases like medical imaging, where full data labeled is really a big challenge. The fourth area we have covered is choosing the right model for your work. It depends on data type, labeling availability, and specific goals. Learn which approach best meets your needs. Okay, let's proceed further. You reached the end of this video segment. Let me put summary for you. Supervised and unsupervised learning are foundational techniques in machine learning, each offering unique benefits. Supervised learning uses label data to make the prediction and classify data into specific categories, making it ideal for accurate outcomes like identifying a spam or predicting prices. On the other hand, unsupervised learning discovers hidden patterns in unlabeled data, often used in applications like customer segmentation and market basket analysis. The video also introduces semi-supervised learning, middle ground between supervised and unsupervised, a blend of both techniques, perfect for handling large data sets with limited labeled information as seen in medical imaging systems. Learn how to choose the best model based on your data and objectives. Here are the key highlights of video. The first is supervised learning, right? How to use the label data to make precise prediction, ideal for classification of, example, spam detection, and regression, example, price prediction. Another highlighted area in this video is unsupervised learning. Discover patterns in unlabeled data commonly used in clustering, example, customer segmentation and association, example, market basket analysis. Another category we have learned in video is semi-supervised learning. So combines both labeled and unlabeled data together, useful for cases like medical imaging, where full data labeled is really a big challenge.
Challenge is to tell me how they're related. They're all space and aviation themed, but that's not it. So here we go. Number one, the distance from the Earth to the Moon is 54 million kilometers. Number two, before I worked at IBM, I worked at a major Australian airline. And number three, the James Webb Telescope took the very first pictures of an exoplanet outside of our solar system. What's the common thread? Well, the answer is that all three facts are an example of an hallucination of a large language model, otherwise known as an LLM. Things like Chat, GPT, and Bing Chat. 54 million K, that's the distance to Mars, not the Moon. It's my brother that worked at the airline, not me, and infamously at the announcement of Google's LLM, Bard, it hallucinated about the Webb telescope. The first picture of an exoplanet was actually taken in 2004. Now, while large language models can generate fluent and coherent text on various topics and domains, they are also prone to just make stuff up. Plausible sounding nonsense. So let's discuss, first of all, what a hallucination is. We'll discuss why they happen, and we'll take some steps to describe how you can minimize hallucinations with LLMs. Now, hallucinations are outputs of LLMs that deviate from facts or contextual logic, and they can range from minor inconsistencies to completely fabricated or contradictory statements. And we can categorize hallucinations across different levels of granularity. Now, at the lowest level of granularity, we could consider sentence contradiction. This is really the simplest type, and this is where an LLM generates a sentence that contradicts one of the previous sentences. So, the sky is blue today. The sky is green today. Another example would be prompt contradiction. And this is where the generated sentence contradicts with the prompt that was used to generate it. So if I ask an LLM to write a positive review of a restaurant and it returns, the food was terrible and the service was rude, that would be in direct contradiction to what I asked. Now, we already gave some examples of another type here, which is factual contradictions. And these factual contradictions or factual error hallucinations are really just that, absolutely nailed on facts that it got wrong. Barack Obama was the first president of the United States, something like that. And then there are also nonsensical or otherwise known as sort of irrelevant kind of information-based hallucinations, where it just puts in something that really has no place being there, like the capital of France is Paris. Paris is also the name of a famous singer. Okay, thanks. Now, with the question of what LLM hallucinations are answered, we really need to answer the question of why. And it's not an easy one to answer, because the way that they derive their output is something of a black box, even to the engineers of the LLM itself. But there are a number of common causes. So let's take a look at a few of those. One of those is data quality. Now, LLMs are trained on a large corpora of text that may contain noise, errors, biases, or inconsistencies. For example, some LLMs were trained by scraping all of Wikipedia and all of Reddit. Is everything on Reddit 100% accurate? Well, look, even if the training data was entirely reliable, that data may not cover all of the possible topics or domains that LLMs are expected to generate content about. So LLMs may generalize from data without being able to verify its accuracy or relevance, and sometimes it just gets it wrong. As LLM reasoning capabilities improve, hallucinations tend to decline. Now, another reason why hallucinations can happen is based upon the generation method. Now, LLMs use various methods and objectives to generate text, such as beam search, sampling, maximum likelihood estimation, or reinforcement learning. And these methods and these objectives may introduce biases and trade-offs between things like fluency and diversity, between coherence and creativity, or between accuracy and novelty. So, for example, beam search may favor high probability but generic words over low probability but specific words. And another common cause for hallucinations is input context. And this is one we can do something directly about as users. Now, here context refers to the information that is given to the model as an input prompt. Context can help guide the model to produce the relevant and accurate outputs, but it can also confuse or mislead the model if it's unclear or if it's inconsistent or if it's contradictory. So, for example, if I ask an LLM chatbot, can cats speak English? I would expect the answer, no, and do you need to sit down for a moment? But perhaps I'd just forgotten to include a crucial little bit of information, a bit of context, that this conversation thread is talking about the Garfield cartoon strip, in which case the LLM should have answered, yes, cats can speak English, and that cat is probably going to ask for second helpings of lasagna. Context is important, and if we don't tell it we're looking for generated text suitable for an academic essay or a creative writing exercise, we can't expect it to respond within that context. Which brings us nicely to the third and final part. What can we do to reduce hallucinations in our own conversations with LLMs? So, yep, one thing we can certainly do is provide clear and specific prompts to the system. Now, the more precise and the more detailed the input prompt, the more likely the LLM will generate relevant and, most importantly here, accurate outputs. So, for example, instead of asking, what happened in World War II? It's not very clear, it's not very specific. We could say, can you summarize the major events of World War II, including the key countries involved and the primary causes of the conflict? Something like that that really gets at what we are trying to pull from this. And that gives the model a better understanding of what information is expected in a response. We can employ something called active mitigation strategies. And what these are using some of the settings of the LLM, such as settings that control the parameters of how the LLM works during generation. A good example of that is the temperature parameter, which can control the randomness of the output. So a lower temperature will produce more conservative and focused responses, while a higher temperature will generate more diverse and creative ones. But the higher the temperature, the more opportunity for hallucination. And then one more is multi-shot prompting. And in contrast to single-shot prompting, where we only give one prompt, multi-shot prompting provides the LLM with multiple examples of the desired output format or context, and that essentially primes the model, giving a clearer understanding of the user's expectations. By presenting the LLM with several examples, we help it recognize the pattern or the context more effectively, and this can be particularly useful in tasks that require a specific output format, so generating code, writing poetry, or answering questions in a specific style. So while large language models may sometimes hallucinate and take us on an unexpected journey 54 million kilometers off target, understanding the causes and employing the strategies to minimize those causes really allows us to harness the true potential of these models and reduce hallucinations.
Hi. So by now, let me summarize the video for you. Discover how to handle. You have discovered how to handle AI hallucination effectively by learning 5 essential prompting techniques that help large language models generate accurate and relevant response, from controlling creativity with temperature adjustment to focusing on a specific task with role assignment. These methods guide AI to reduce errors and avoid misinformation. This video highlights why addressing hallucination is crucial to building trustworthy AI interaction, especially for business and technical applications. Right? Let me come with the key points which we have understood. AI hallucination. We also understood types of AI hallucination. We also understood prompting techniques like temperature control, role assignment, specificity, and few short example, then content controlling, content grounding, and then instruction-based prompting. So overall, as a benefit, we are able to reduce misinformation of our large language model. We also help to avoid legal actions, legal issues, and foster trust in AI-driven solution. I hope you are okay with these kind of concepts until now. And if so, let's proceed further. Hi. So by now, let me summarize the video for you. Discover how to handle. You have discovered how to handle AI hallucination effectively by learning 5 essential prompting techniques that help large language models generate accurate and relevant response, from controlling creativity with temperature adjustment to focusing on a specific task with role assignment. These methods guide AI to reduce errors and avoid misinformation. This video highlights why addressing hallucination is crucial to building trustworthy AI interaction, especially for business and technical applications. Right? Let me come with the key points which we have understood. AI hallucination. We also understood types of AI hallucination. We also understood prompting techniques like temperature control, role assignment, specificity, and few short example, then content controlling, content grounding, and then instruction-based prompting. So overall, as a benefit, we are able to reduce misinformation of our large language model. We also help to avoid legal actions, legal issues, and foster trust in AI-driven solution. I hope you are okay with these kind of concepts until now. And if so, let's proceed further. Hi. So by now, let me summarize the video for you. Discover how to handle. You have discovered how to handle AI hallucination effectively by learning 5 essential prompting techniques that help large language models generate accurate and relevant response, from controlling creativity with temperature adjustment to focusing on a specific task with role assignment. These methods guide AI to reduce errors and avoid misinformation. This video highlights why addressing hallucination is crucial to building trustworthy AI interaction, especially for business and technical applications. Right? Let me come with the key points which we have understood. AI hallucination. We also understood types of AI hallucination. We also understood prompting techniques like temperature control, role assignment, specificity, and few short example, then content controlling, content grounding, and then instruction-based prompting. So overall, as a benefit, we are able to reduce misinformation of our large language model. We also help to avoid legal actions, legal issues, and foster trust in AI-driven solution. I hope you are okay with these kind of concepts until now. And if so, let's proceed further. Hi. So by now, let me summarize the video for you. Discover how to handle. You have discovered how to handle AI hallucination effectively by learning 5 essential prompting techniques that help large language models generate accurate and relevant response, from controlling creativity with temperature adjustment to focusing on a specific task with role assignment. These methods guide AI to reduce errors and avoid misinformation. This video highlights why addressing hallucination is crucial to building trustworthy AI interaction, especially for business and technical applications. Right? Let me come with the key points which we have understood. AI hallucination. We also understood types of AI hallucination. We also understood prompting techniques like temperature control, role assignment, specificity, and few short example, then content controlling, content grounding, and then instruction-based prompting. So overall,
Like ChatGPT are examples of foundation models, large reusable models that have been trained on vast amounts of knowledge on the internet, and they're super flexible. The same large language model can analyze a legal document or write a poem about my soccer team. But what if we want to improve the performance of pre-trained LLMs or large language models to address a specialized task? Well, until recently, the best way to do that was using a method that is known as fine tuning. Now, with fine tuning, you gather and label examples of the target task, lots and lots of examples, and you fine-tune your model rather than train an entirely new one from scratch. But there's a simpler, far more energy-efficient technique that has emerged in place of fine-tuning, and that is known as prompt tuning. So what is prompt tuning? Well, prompt tuning allows a company with limited data to tailor a massive model to a very narrow task. And there's no need for gathering thousands of labeled examples like we have to do with fine-tuning. In prompt tuning, the best cues or front-end prompts are fed to your AI model to give it task-specific context. The prompts can be extra words introduced by a human, or more commonly an AI-generated number introduced into the model's embedding layer to guide the model towards a desired decision or prediction. Now, if all this sounds a little bit familiar, using prompts to guide the output of an LLM, that's because it most certainly is. That is an example of something else called prompt engineering. Now, prompt engineering is the task of developing prompts that guide an LLM to perform specialized tasks. Honestly, it sounds like a lot of fun. I think I'd quite like to be a prompt engineer one day. So if I want my LLM to specialize as an English to French language translator, I might engineer a prompt to do so. So my prompt might start with, let's say translate, and we want to translate English to French. That's the task description of my prompt. Then I'm going to add some few shot examples. So let's add those now. So here's the English word bread into the French word pain. That's one shot example. Let's add another. Butter, we're going to turn that into beurre. And then the next part of my prompt, I'm going to add the word that I want it to translate next. So cheese, and that's it. Now prompts like this, written by a human, me, Mr. Wannabe prompt engineer himself, they prime the model to retrieve the appropriate response from the LLM's vast memory, in this case specifically for other words in French. And the model's output is its prediction. What is this model going to output? Fromage. That worked. We've used prompt engineering to train a model to perform a specialized task with just a single prompt introduced at inference time without needing the model to be retrained. But if the task is more complex than this, it may require dozens of these prompts, and so these handcrafted prompts have begun to be replaced by AI designated prompts known as soft prompts. Now, soft prompts have been shown to outperform human-engineered prompts, which we can know now as hard prompts. These were hard-coded by a human. This is not good news for my prompt engineering career, because you see, unlike hard prompts, AI-designed soft prompts, they're used in prompt tuning, and they are unrecognizable to the human eye. Each prompt consists of an embedding, or strings of numbers that distill knowledge from the larger model. And these soft prompts can be high-level or task-specific and act as a substitute for additional training data and are incredibly effective in guiding the model towards the desired output. But do keep in mind that one drawback of prompt tuning and soft prompts in general is its lack of interpretability. That means that the AI discovers prompts optimized for a given task, but it often can't explain why it chose those embeddings. Like deep learning models themselves, soft prompts are opaque. All right, so let's consider we have here a pre-trained model. So this might be a large language model, something like that. Okay, now let's consider three options for tailoring this pre-trained model for specialization. And I'm going to talk about the three that we've covered here. So first of all, fine-tuning. Fine-tuning. So with fine-tuning, we take this pre-trained model and we supplement it. We supplement it specifically with tunable examples. These are the thousands of examples that I talked about right at the beginning. Once we've done that, we can then provide our input data into the model, and it should now be able to perform our specialization. So that's fine-tuning. What about prompt engineering? How is that different? Well, with prompt engineering, we take the model as it is. We haven't tuned it, and then we add in an additional prompt. So we have our input prompt, but we also add into that input prompt an engineered prompt which sits in front of it. So we effectively provide two prompts here for the specialization. That's what we did with our language translator. So we provided this pre-written engineered prompt, and then we provided our input, which was cheese. So that's prompt engineering. What about prompt tuning? How is that different? Well, with prompt tuning, again, we use the pre-trained model as it is, and we again provide an input, but we also provide something in front of that input, and that is the tunable soft prompt that is generated by the AI itself. And it's the combination of these two things that allow us to use the model in a specialized way. Prompt tuning is proving to be a game changer in a variety of areas. For instance, in multitask learning, where models need to quickly switch between tasks, researchers are finding ways to create universal prompts that can be easily recycled. Techniques like multitask prompt tuning allow the model to be adapted swiftly and for a fraction of the cost of retraining. Prompt tuning is also showing promise in the field of continual learning, where AI models need to learn new tasks and concepts without forgetting the old ones. Essentially, prompt tuning allows you to adapt your model to specialized tasks faster than fine-tuning and prompt engineering, making it easier to find and fix problems. My career as a prompt engineer might be over before it started, so I guess it's back to the drawing board, or rather, fair warning, if you're feeling a little hungry right now, you might want to pause this video and grab a snack before continuing, because I'm going to explain the difference between machine learning and deep learning by talking about pizza. Delicious, tasty pizza. Now, before we get to that, let's address the fundamental question here. What is the difference between these two terms? Well, put simply, deep learning is a subset of machine learning. Actually, the hierarchy goes like this. At the top, we have AI, or artificial intelligence. Now, a subfield of AI is ML, or machine learning. Beneath that, then we have NN, or neural networks, and they make up the backbone of deep learning algorithms, DL. And here on the IBM Technology channel, we have a whole bunch of videos on these topics. You might want to consider subscribing. Now, machine learning algorithms leverage structured, labeled data to make predictions. So let's build one, a model to determine whether we should order pizza for dinner. There are three main factors that influence that decision, so let's map those out as inputs. The first of those inputs we'll call X1. And X1 asks, will it save time by ordering out? We can say yes with a 1 or no with a 0. Yes, it will, so X, that equals 1. Now X2, that input says, will I lose weight by ordering pizza? That's a 0. I'm ordering all the toppings. And X3, will it save me money? Actually, I have a coupon for a free pizza today, so that's a 1. Now, look, these binary responses, 1s and 0s, I'm using them for simplicity, but neurons in a network can represent values from, well, everything to everything, negative infinity to positive infinity. With our inputs defined, we can assign weights to determine importance. Larger weights make a single input's contribution to the output more significant compared to other inputs. Now, my threshold here is 5. So let's weight each one of these. W1, well, I'm going to give this a full 5 because I value my time. W2, this was the will I lose weight one. I'm going to rate this a 3 because I have some interest in keeping in shape. And for W3, I'm going to give this a 2 because either way, this isn't going to break the bank to order dinner. Now, we plug these weights into our model, and using an activation function, we can calculate the output, which in this case is the decision to order pizza or not. So to calculate that, we're going to calculate the y hat, and we're going to use these weights and these inputs. So here we've got 1 times 5, we've got 0 times 3, and we've got 1 times 2. And we need to consider as well our threshold, which was 5. So that gives us, if we just add these up, 1 times 5, that's 5, plus 0 times 3, that's 0, plus 1 times 2, that's 2, minus 5. Well, that gives us a total of positive 2. And because the output is a positive number, this correlates to pizza night. Okay, so that's machine learning, but what differentiates deep learning? Well, the answer to that is more than 3. As in, a neural network is considered a deep neural network if it consists of more than 3 layers, and that includes the input and the output layer. So we've got our input and output, we have multiple layers in the middle, and this would be considered a deep learning network. Classical machine learning is more dependent on human intervention to learn. Human experts, well, they determine a hierarchy of features to understand the differences between data inputs. So if I showed you a series of images of different types of fast food, like pizza, burger, and taco, you could label these in a data set for processing by the neural network. A human expert here has determined the characteristics which distinguish each picture as the specific fast food type. So for example, it might be the bread of each food type might be a distinguishing feature across each picture. Now this is known as supervised learning because the process incorporates human intervention or human supervision. Deep machine learning doesn't necessarily require a labeled data set. It can ingest unstructured data in its raw form, like text and images, and it can automatically determine the set of features which distinguish pizza, burger, and taco from one another. By observing patterns in the data, a deep learning model can cluster inputs appropriately. These algorithms discover hidden patterns of data groupings without the need for human intervention, and they're known as unsupervised learning. Most deep neural networks are feed-forward. That means that they go in one direction, from the input to the output. However, you can also train your model through something called backpropagation. That is, it moves in the opposite direction from output to input. Backpropagation allows us to calculate and attribute the error associated with each neuron and allows us to adjust and fit the algorithm appropriately. So when we talk about machine learning and deep learning, we're essentially talking about the same field of study. Neural networks, they're the foundation of both types of learning, and both are considered subfields of AI. The main distinction between the two are the number of layers in a neural network, more than 3, and whether or not human intervention is required to label data. Pizza, burgers, tacos, yeah, that's enough for today. It's time for lunch. And before I go, if you did enjoy this video, here are some others